All right. So the first thing we could talk about is bond properties. So we got how many bonds? What kind of bonds? Try it. Are you sure?
Yep.
Positive.
100%.
100% positive.
Metallic, ionic, and covalent.
Oh my
Unless
god.
you want to kind of count what we did yesterday and count hydrogen bonds.
What?
Unless you want to include hydrogen.
Count hydrogen bonds? Is that what you said? That's not a no. That's not doesn't work.
Hydrogen bonds and diplo are polar,
Dipole.
and dipole are polar.
Ionic, covalent, and what's the other one?
Van de Cleef is whatever.
Nope.
That's not polar. Van de Peel.
Vanderpeel. You're a funny guy. Now, ionic, those bond properties. All right. Think about how ionic bonds form. Okay. What do they do? You've got one atom that shoots off an electron to another one. The other atom takes the electron, takes it up, sucks it up, and that becomes negative. The one that shot out the electron is now positive. And it joins together in this, what we call an electrostatic attraction, which means that they're just attracted to the opposite side. So it's like this. This represents one of the atoms that's positive. This one represents the negative atom. This one's a positive, that one's a negative. And we can keep on going with this in this giant structure that we call, what do we call this giant structure? It's not a molecule, it's a...
Oh, it's a chart.
It's a...
No, I know.
It's a...
Table. No,
I think it's a French word.
The tab.
It's a... Keep guessing. I can be here all day.
The Soleil.
What is this thing called? When you got a whole bunch of these ionic...
Chart.
Keep going. A whole bunch of ionic bonds, when they're coming together, they're not called molecules, they're called...
Covalence. Bonds. Melting point. Solubility.
Anybody else? You can look in your notes. Actually.
Crisscross applesauce.
You get 5 more guesses. It's at the very beginning of your packet.
What are you filming?
What?
Electron.
Nope. That's one. What's that?
Lattice.
Lattice or lattice. Yes.
Wait, I'm
Lattice.
missing that page.
No, you're not.
Probably not.
Lattice.
Lattice.
This thing's called a lattice.
What page lettuce on?
It's not lettuce. That's something you eat. That's what rabbits eat. And turtles. You ever had a turtle that eats lettuce?
And the iguana we're getting.
I know,
in.
And the iguana and the gecko.
Yes.
The gecko that you're getting. That could eat lettuce too. Maybe. I don't know.
You can get it.
Just a joke. So we've got this lattice right here. This lattice has a bunch of positives and negatives all lined up in this in these rows. Now, what happens here is that this thing can be dissolved. It can be dissolved in water. So you can dissolve it in water. And when it's dissolved in water, you guys all know that what? It conducts what? Electricity. Yes. It conducts electricity when it's dissolved in water. It's also got a very, 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 is it a high or low melting point? I forget. Oh yeah, it's a high melting point. And what else? What other properties does it have? It doesn't conduct electricity as a solid. Ever.
So when we did this, what was it, the
The quest.
Quest.
Yes.
There was the last question. There was one question where there was one that conducts very little while it's
Right.
solid, and
Yeah.
when it's dissolved in water. What was
Yes.
that? Was
When
that
the-
metallic?
Yeah.
Yeah?
Yeah.
So metallic does
Metallic conducts electricity as a solid. Yes.
in water too.
In water, well, it doesn't dissolve in water. That's the problem.
But it's
So in
still-
that problem, you could have either one of those would make sense. That's what I want you to think. Kind of press yourself a little bit and say, well, it could be this, it could be that, but I'm not really sure. So it's I wanted that ambiguity. Metals, they don't dissolve in water. They just stay as a solid. Metals are in this. You've seen this before, where you have like the positive nuclei, and now I'm going to make the little electrons swimming around here. Here's a positive nuclei.
That's
Here's a
a little
positive
cool,
nuclei,
right?
and they have these electrons
It's a pool of
swimming around.
electrons?
It's a sea of electrons. Nice. A sea of electrons, and they're all swimming around. This makes a very special property. You can have electricity conducted right through these metal substances, and you can also have heat conducted right through that metal. and you can see this anytime in real life when you just touch a hot stove with touch the handle of a metal thing on a hot stove. It's gonna hurt, right? So that conducts electricity. It conducts heat. It's malleable because you can kind of smoosh this in one direction, but it doesn't break. It's not very brittle. Over here, the lattice is pretty brittle because if you put enough pressure on it, it'll crack. It'll break. That's what happens with a lattice. What else? What else can we talk about this? Melting point? Is it a high or low melting point? It's a high melting point. That's right. And covalent, let's talk about that one as the last one. Covalent, that's like the sugar. So whenever you think about covalent bonds, think about sugar. And what happens with the sugar when we put a lot of heat into it? It melted. So it's got a low melting point. Did it dissolve in water?
No.
Yes.
It did. So sometimes covalent things can dissolve in water. Like sugar water is covalent bonds that are dissolved in water. It can happen, but sometimes, sometimes it doesn't happen. So it could be either one. It could dissolve in water or it could not dissolve in water. It's just one of the properties of covalent bonds. It's not a strict rule for that. Okay?
And then ionic is high melting point or low melting?
We just went through this. It's high melting point. Okay? All right. All right, that's the bond properties. Now let's talk about naming covalent bonds. Let's say that you have first of all, just recognizing covalent bonds. So is this a covalent bond?
No.
No, that's not a covalent bond. That's an ionic bond. Is this a covalent bond?
On the test, are we gonna have a periodic table?
No, that's an ionic bond. Is this an ion? Oh wait, I could just keep doing this all day. I'm just gonna do this. P. Let's just say P. I'm totally making this up. P.
Yes.
PCl3.
Covalent.
Covalent. Oh my God, that's covalent.
Like the
It's
number.
covalent.
On the test, are we gonna have a periodic table with the different colors? Or?
You also have a list of mono, di, tri, all that stuff. Mono, di, tri, tetra,
Oh, okay.
all the
Are we
prefixes.
also gonna have a list for the best?
Yes, you'll have that list too. So this, Alex, I need your attention. This right here, that P is what? That's phosphorus. Now, normally with the naming conventions, you have a prefix for each element here. But in this case, there's only one phosphorus, so we would have written mono, but since it's the first element here, we drop it. There's no mono in the first one. Okay, so now this is going to be mono, not mono, sorry, phosphorus, and then it's trichloride. Yes, because there are three right there. Okay, and that's all you do for covalent bond naming is you just literally translate what you see into the words, and vice versa. If you had something else that was like, I don't know, heptacarbon nanohydride. Just imagine you have that. Heptacarbon nanohydride.
Nano or mono?
C7, H9. I think known as 9, right?
Okay? So all you're doing is you're taking the prefixes and you're just translating them into numbers. That's not a ha, that's a 9. H9 hydride. Right there. And this is carbon. Okay?
So covalent is two nonmetals.
2 nonmetals, that's correct.
And ionic is one more.
And ionic is a nonmetal and a metal.
Can there be a covalent with transition metal?
Can there be a covalent with a transition metal? Well,
no, there can't be, right?
no,
They're all
because
metals.
that would be a metal with a nonmetal. Yeah.
So for ionic bonds, when we name them,
Mhm.
let's say even if it's like Na3Cl,
Yes.
we won't have a prefix or anything. We'll just write like sodium chloride. And that's it.
Right.
The
For-
only complicated one is when it's transition.
Right. This is a good rule to think about. So this can save you a lot of time, and I'll see a lot of people doing this, and a lot of points too. So if you have let me just this is just a little mock-up of a periodic table. Okay, let's imagine that you have something and you know it's a metal and a nonmetal. Yeah, a metal and a nonmetal. Unless it's in here, you don't have to worry about any kind of prefixes, any kind of parentheses, any kind of anything. If you have a metal and a non-metal, like let's say that this right here, these are all metals, those are all metals. Okay? You don't have to worry about the prefixes, you don't have to worry about any parentheses.
Wait, there's only prefixes if it's transition metal?
No, there's prefixes if it's two non-metals. Those are covalent. These are non-metals right over here. These are metals. These are metals too, but they're transition metals.
What does it mean, like transition metals? Like, what's really the difference?
The difference between them is that they have extra places for basically it's like they've got extra pockets for electrons, so they can store more electrons, which also gives them those weird properties. What else? These are metals over here. So if you've got just a regular metal and it's not a transition metal, it's like, let's say like I don't know, what's a regular metal? Calcium. Calcium. This calcium. What would this be?
Bromide.
Calcium bromide. That's it. You don't need to worry about any other things. The biggest mistake I saw on the test, on the quest, was that people wanted to stick a little parenthesis right there because they're like, oh my god, it must mean that this has to give a certain amount. No, you don't need to worry about that if it's a regular metal. If it's a transition metal, that's when you have to worry. You have to think about, oh, how many electrons is this transition metal giving? Because it could give up to different kinds of electrons, or different amounts of electrons. So in that case, for transition metals, because that's one thing we want to talk about here, so we've done that. We want to name transition metals now. How do we do that? Well, we have to think about, first, how many electrons this sucker needs. So let's now change this situation. Let's say instead of calcium bromide, we have something like iron bromide. I'm just going to write out, I'll do Fe, and I'm going to do Br. Let's do Br2. Let's just keep it the same. Okay. FeBr2. Now, that Fe should just like hit you in the face. That Fe, is that a transition metal?
Yes.
Yes, it's a transition metal. It's in the transition metal box. So, since it's a transition metal, it could give up to different electrons, different numbers of electrons. So, we can write out the iron, and then we can write out the bromide, but we need to know how many electrons this iron is giving. And to do that, I know you know the answer, but I just want to walk through this a little bit more slowly. To do that, we need to know how many total electrons this bromine over here is taking. Total electrons. So how many does this take? How many does this one single bromine takes? How many?
1.
Right, it takes 1. But we've got this 2 over here. That means totally takes 2. Right? So bromine totally takes 2. So how many must iron give to bromine?
2.
Right. So this must give 2. So we write a Roman numeral 2 right there. Perfect. Confused?
No.
Okay. Let's make it more difficult. Ready? I'm going to say it's now Fe. FeO. Let's do Fe2O.
Oxygen.
First of all, this name is going to not be bromide anymore. What's it going to be?
Oxide.
Oxide. This one is a lot more difficult.
So it's 3.
So oxygen, how many does it need totally?
6.
2. Well, it needs 2.
It needs 2.
Is it
Why does it need 2? Why does it take 2?
valid
Let's
shell
keep
has
this
only
the same.
6, so to fill it up, you need 2 more.
It takes 2.
Oh.
Right. It's in the 6th group over here. It needs another 2 to complete its octet.
But if there's 2 iron, that means it have to take 4.
1.
Right. So now you have to think about this. You've got this whole thing is taking 2 electrons, but we've got 2 irons that are giving away
each iron
electrons.
gives 1.
So each iron is giving how many?
1.
Each iron gives 1. This is the confusing part right here, right? So